Now, illustration number 7.14. The angular speed of motor wheel is increased from 1200 rpm to 3120 rpm in 16 seconds. What is the angular acceleration? Assuming the acceleration to be uniform, how many revolutions does the engine make during this time? Now see, the values here which are given, they are in rpm. So initial angular speed is 1200 rpm, and if you convert it into radian per second, then 1200 multiplied by 2 pi, it is rpm means rotations per minute, so divided by 60. Okay, so we will have 40 pi radian per second. Similarly, the final one is 104 pi radian per second, and angular acceleration is omega minus omega 0 upon t, and these values if I substitute, then you get 4 pi radian per second square. Very easy calculation. Okay, now angular displacement we want to calculate in 16 seconds, so that angular displacement theta is omega 0 t plus 1 half alpha t square. Values are there, that of omega 0, time is 16 seconds. Okay, alpha we got 4 pi radian per second square, and time is 16 seconds. And if you simplify, okay, then you will have the angular displacement. Okay, you will find the angular displacement. Okay, or initially you find angular displacement. Now say if one rotation, try to understand, one rotation will give you the angular displacement of 2 pi. So if there are n number of rotations, then the n is the number of rotation. So total angular displacement will be 2 pi n. Let us consider that there are n number of rotations, and one rotation is equal to 2 pi is the angular displacement. So total angular displacement will be 2 pi n. So instead of this theta, it is written as 2 pi n, and this is simplified. Okay, and you get the number of revolutions directly, and that is 576. Okay, now example number 7.15. Okay, a cord of negligible mass is wound around the rim of a flying wheel of mass 20 kg and radius 20 centimeter. A steady pull of 25 Newton is applied on the cord as shown in the figure. The flywheel is mounted on a horizontal axle with frictionless bearings. We want to compute the angular acceleration of the wheel. Find the work done by the pull when 2 meters of the cord is unwound. Find also the kinetic energy of the wheel at this time. Assume that the wheel starts from rest, and compare answer of part B and C. Now see, here this is the flywheel, and the axle is passing through its center C. Radius is 20 centimeter, so you can write 0.2 meter. Mass of this flywheel is 20 kg. Okay, here 25 Newton force is applied, so this will start rotation. Okay, and torque is equal to Rf sin theta. Now try to understand, this is the radius vector and this is the force. Angle between them is 90 degree. So Rf sin 90 it will become, and you will have torque to be 5 Newton meter if you substitute these values of R, which is 0.2, and F is 25 Newton. Okay, the moment of inertia is mr square by 2, that of what you call it, we are given here the flywheel. Okay, so its moment of inertia is mr square by 2. Okay, A table is given in the textbook and you have to see the moment of inertia of different types of objects. Okay, and flywheel is a circular disc, and the circular disc is having the moment of inertia which is mr square by 2. So you can easily calculate the moment of inertia of this flywheel is a kind of disc. Okay, so its moment of inertia is given in that table mr square by 2. Okay, then its moment of inertia is 0.4 kilogram meter square. Now torque is I alpha. Okay, so you can easily calculate the value of alpha, that is angular acceleration, to be, okay, alpha is equal to tau upon I. Okay, so you place the values there and get the answer of alpha to be 12.5 radian per second square. And work done by this pull, because it is unwinding the thread by 2 meter. So force into displacement, force is 225 Newton and 2 meter is the displacement, so we will have work done to be 50 joule. Now let us consider that final angular velocity is omega, therefore kinetic energy which is gained, initially it was at rest, so initial angular velocity omega 0 is 0 radian per second. Okay, so final angular velocity is omega, so kinetic energy is 1 half I omega square, and omega square minus omega 0 square is equal to 2 alpha theta, so omega square can be 2 alpha theta because omega 0 is 0 initial angular velocity. Okay, now theta we find, theta can be calculated as length of unwound string divided by radius of the wheel, because whatever amount of length of the string is unwound, that will be the arc. Try to understand, that will be arc, and arc is equal to radius multiplied by theta. Okay, and theta can be found as arc, that is length of unwound string divided by the radius of the wheel. Length of unwound string is 2 meter and radius is 0.2, so theta, that is equal to 10 radian. Okay, now omega square is equal to 2 alpha theta, as you know. Okay, so you can find omega square here. Okay, 2 alpha is already calculated, theta we got 10 radian, so 250 radian per second, because it is square, that is why the square is taken here. Now directly you can write this omega square in this formula. Kinetic energy is 1 half I omega square. So instead of omega square you can use this 250. I is 0.4 and kinetic energy is obtained, that is 50 joule, which is same as the kinetic energy. Okay, so kinetic energy gained by the wheel is equal to work done by the force. So both the values which you are getting here, they are same. Here also we are having 50 joule. Okay, and according to other calculation also, okay, we have this kinetic energy to be 50 joule. Here there is no loss of energy due to friction. Okay, now we have 7.16. Okay, there are three different types of bodies: a ring, solid cylinder and solid sphere. Roll down the same inclined plane without slipping. They start from rest. The radii of the bodies are identical, means they are having same radii. Which of the bodies reaches the ground with maximum velocity? Now try to understand first of all the velocity at what they are reaching at the ground. We have already calculated as such in the theory, that whenever this object of radius r is at highest point, say at height h, then it has the energy mgh. Now when it rolls down, okay, and it reaches at this final position, then the potential energy which was mgh is converted into two types of kinetic energy. One is rotational kinetic energy and the other one is translational kinetic energy. And if in general let the moment of inertia of this object is I, then its rotational kinetic energy will be 1 half I omega square, and its final velocity when reaches here is v. Okay, then its kinetic energy at the bottom is 1 half mv square. So 1 half I omega square is the rotational kinetic energy and 1 half mv square is the translational kinetic energy at the bottom. Here omega is the final angular speed at the bottom of the inclined plane. Okay, so this way it is calculated. અગાઉ આપણે ગણેલું છે, we have calculated already. So mgh is equal to 1 half I omega square plus 1 half mv square, and as you know I is equal to mk square, so 1 half mk square is equal to omega square. Okay, sorry, I is mk square, so instead of I we write mk square into omega square, so 1 half mk square into omega square plus 1 half mb square, and as you know v is equal to r omega, so omega is equal to v upon r, so instead of omega we are writing v upon r here. Okay, k square is there. Okay, so m will be cancelled out, you can see very easily. Okay, here m is cancelled out. Okay, and here instead of omega it is v upon r, so v square upon r. Okay, so 1 half k square v square upon r square plus 1 half v square it remains. Now 1 half v square is taken common. Okay, so in bracket 1 plus k square upon r square it remains. Okay, 2 is multiplied with this gh, so it becomes 2gh, and v square is then made a subject of formula. Okay, so we will have 2gh upon this value, that is 1 plus k square upon r square, and if you find v, then it will be the square root of this, that is under root of 2gh upon 1 plus k square upon r square. Okay, now see from the table, now we will take the radius of gyration for different objects. Okay, now radius of gyration for ring is k is equal to r, so k square will be r square, so instead of this k square we shall write r square, so r square and r square will be cancelled out, we will have 1, and this one and this one which we got will become 2. Okay, so very easy to calculate now, 2 and 2 will be cancelled out. Okay, so under root of gh will be the speed of the ring when it reaches at the bottom of the inclined plane. Now for the solid sphere, okay, for the solid sphere we will have k is equal to r upon root 2. Okay, now for the solid cylinder as such, this is not the sphere, try to understand, this is a misprint here, this is not for the sphere, it is for the cylinder. Okay, and for the cylinder it is k is equal to r upon root 2, so k square will be r square upon 2, and if you write this value in the equation which we got, that of the speed, this is our general equation. Okay, where there is a k square, we shall write r square upon 2, so r square and r square will be cancelled out. Here it is simplified. See, instead of that k square we have written r square by 2, so this r square are cancelling out, so we will have 1 by 2, 1 plus 1 by 2 is 3 by 2. Okay, so this becomes 3 by 2, 2 will go in the numerator and it will be multiplied with 2gh, so 2 into 2gh it becomes, and in the denominator it becomes 3 and square root of this whole term. Okay, so it is simplified here 4 gh upon 3, and square root of it will be the speed of cylinder. Okay, now for the solid sphere, now it is for the solid sphere. Okay, it was earlier the misprint was there. Now here it is k is under root 2 by 5r, so k square will be 2 by 5r square, and instead of k square you write 2 by 5r square, so it becomes 2r square upon 5. This r square will be cancelled out, and 5 is LCM, so it becomes 5 into 2gh, because 5 goes up in the denominator, 5 plus 2 and square root of 8, so it becomes 10gh. Okay, 10gh upon 7, and square root of it will be the answer. Okay, so this way we will have the different speeds of the objects when they are reaching at the bottom, and sphere has the greatest and the ring has the least speed of the center of mass at the bottom of the inclined plane. So solid sphere reaches at first to the bottom of the slope. Okay, thank you very much. Try to solve this 2-3 times, okay, in your notebook.